It's already 15 minutes because it's okay. So today what we'll see is already we have finished like second and third blocks of your this paper. That is block 2, block 3. We have finished atomic spectra as well as this molecular spectra. Both we have finished. Then we have to move for IR and Raman spectra. So in this, first we'll discuss about Raman spectra. Block 4. We'll go for Raman spectra. Okay. So 1 minute. I'll right. One minute. It's one minute. It is not writing. So today we'll see about Raman spectra. Right. So we will see about Raman spectra now. So it's okay now. So in the case of the Raman spectra, before going into study about the Raman spectra, so we should know about the Relic scattering. Then after we'll see the Raman scattering. So why we required this all we'll see here. So first of all, if you if some photons are there, if these photons, if they are interacting with the molecules of matter in number of ways. Okay, so the photons can be interact with the molecules of matter in number of ways. So when these photons strike the solid or collection of molecules or of any matter, whenever these photons are striking, then what happens means most of these are scattered elastically. Okay, most of these are scattered elastically. Otherwise, we can say that when a beam of monochromatic light is passed through a gas or liquid or transparent crystal or any transparent solid, whatever matter if you are having, then what happens means a small fraction of light is scattered in all directions. Okay, a small fraction of light is scattered in all directions. The scattered light can be seen from the sides of the substances. So this is observed by Rayleigh. So Rayleigh observed that in this spectrum of scattered light, there is a change in the intensity. Okay, he observed that there is a change in the intensity, but there is no change in wavelength or frequency. Okay, there is no change in the wavelength or frequency has been observed. So this scattering is called as a Rayleigh scattering. So what is that? So when a beam of monochromatic light, whenever it is passed through a gas or liquid or a transparent crystal or transparent solid, whatever we have, then a small fraction of light is scattered in all directions. The scattered light can be seen from the sides of the substances. So this Rayleigh is observed that in this spectrum of scattered light, so there is no change. There is a change in intensity. There is a change in intensity, but there is no change in the wavelength or frequency. Okay, so he didn't observe any change in the wavelength or frequency, but he has observed that there is a change in the intensity, and this type of scattering is called it as a Rayleigh scattering. So what he has seen is there is no change. Okay, there is no change in frequency. Okay, in frequency or what we call wavelength. So there will be no change in these two, whereas there is a change in the intensity, and this scattering is called it as what Rayleigh scattering has been called. Okay, Rayleigh scattering has been called. So then after, in the year 1928, Sir C.V. Raman, okay, Sir C.V. Raman, he observed that the spectrum of scattered light, okay, the spectrum of scattered light consisting of frequencies of greater and as well as the smaller than incident beam frequency. That is, whenever the monochromatic light is incidenting onto the matter, Sir C.V. Raman observed that there is a there is a change of frequencies of greater and smaller. Okay, that means greater than and smaller than the incident beam frequency. Suppose if you have said that a incident beam of light is having a frequency of X, then he observed that there is a change in the frequency more than X and as well as the less than X. That is, greater and smaller than the incident beam frequency he has been observed. And this is what he called it as, otherwise this is known as what a Raman effect we have been called. Okay, so Raman effect we have been called. So the greater lines, greater frequency lines and as well as the low frequency sides, as we have seen, so they have been called as the strokes and anti-strokes lines respectively. They have been called. Okay, the lines on the low and the high frequency sides of the Rayleigh. So Rayleigh, he observed that there is no change in the wavelength and as well as the frequency. So here Sir C.V. Raman has been observed that there is a change in that one. So the change is like this, like the low and high frequency sides of the Rayleigh line are called strokes and the anti-strokes lines respectively. They have been called. Okay, and the scattered photons, okay, the scattered photons have frequency shifts, characteristics of vibrational as well as the rotational energies of the molecule. Okay, the scattered photons have frequency shifts which are characteristics of the vibrational and as well as the rotational energies of the molecule. So the lines, whichever they have been observed here, it is. Suppose if you draw this one, if you draw this one, so here like this, here we have right. So this is what actually the existing line. Otherwise, we can say that this is the Rayleigh line we can call. So below this, that is nothing but the less frequencies as well as the high frequencies have been observed by the Raman. So here, which we have the frequencies which are less. These are named as a Stokes lines, which are having the less frequency than the what we call Rayleigh frequency. So here again, the lines which are having the greater frequency than the what we call Rayleigh lines, they have been called it as a anti-Stokes lines. Anti-Stokes lines they have been called here. Okay, so if you see from the middle, the difference in the frequencies is delta nu. From here to this side also, there is a change in the frequencies delta nu. That is, so as we said that in the middle, whichever we have, so that is here we said that there is no change of frequency or wavelength has been observed by the Rayleigh, and we called it as a Rayleigh spectrum. And in the Rayleigh scattering, we have the what we call, there is a change in the intensity, but there is no change in the frequency or wavelength. So this, if you consider it as a Rayleigh line of wavelength or frequency, if you consider the lines which are in the case of the Ramans or CV Raman, whichever we have been observed, that is whenever the monochromatic light is interacting in the case of the frequencies, and he observed that there will be greater frequencies to original, you have lesser frequencies to original he has been observed. So this observed frequencies which are having the greater frequency than the original, that is about there is a change in the frequencies delta nu, that is what we called it as a anti-Stokes lines. And the scattering which is having what we call lesser frequencies than the Rayleigh line, we called it as a Stokes lines. So there is a change in frequency less than the original one, that is delta nu you have. Okay, so this is what Raman spectrum, what we call Raman scattering, we can call here. Okay, so in the case of this Raman's spectrum, there are certain important characteristics are there. So he observed that under low resolution, okay, under low resolution, these that is nothing but there is one Stokes Raman line and one anti-Stokes Raman line. Okay, he observed that under the low resolution, there is one Stokes Raman line and as well as the one anti-Stokes Raman line, each having some wave number displacement, that is delta nu. Okay, each having, there is a wave number displacement delta nu with respect to x, that is the exiting line, that is the existing line. So this is vibrational Raman spectrum. Okay, this is what we call it as a vibrational Raman spectrum we call. So Raman displacement delta nu, whichever we have, Raman displacement delta nu agrees exactly with the wave number of the main vibrational rotational absorption. Okay, so this vibrational Raman spectrum, Raman in which Raman displacement delta nu, whichever we have, Raman displacement delta nu, nothing but there is a frequency more than the original delta nu, and there is a less frequency than with Rayleigh, that is delta nu we have. So this vibrational Raman spectrum Raman displacement delta nu agrees exactly with the wave number of the main vibrational rotational absorption. That is main vibrational as well as the rotational absorption. Vibrational, rotational absorption band, which is this vibrational rotational absorption band in the near infrared spectrum of the molecule, in the near infrared spectrum of the molecule. Otherwise, we can say that near infrared. So in the case of the IR, we can say that near infrared spectrum of the molecule. Okay, this is under the low resolution they have seen. This is the first characteristic we have. Okay, so next we have is 1 minute. Next characteristic, that is a second characteristics, whichever second characteristic of the Raman spectrum. So here we consider about the high resolution. In the previous characteristic, we have taken the low resolution. We have been taken here high resolution. We are going to be considered under the high resolution. The that is exciting line is found to have on both sides close approximately equidistant line. Okay, under the high resolution, the what we call exciting line is found to have on both sides close approximately equidistant line. Okay, this is what pure rotational Raman spectrum. We call it as a pure rotational Raman spectrum. We call it as a rotational Raman spectrum. We are going to be called here. Okay, so the separation between the successive lines in the far infrared spectrum. Here, this is observed. In the previous one, we have seen in the case of the low resolution, we have seen that vibrational as well as the rotational absorption we have seen. In this case, it is a pure rotational Raman spectrum here. And here we have that is the spectrum between the successive lines are in the far infrared, far higher. In the previous one, we have seen in the low resolution, in the near infrared region, we have been observed. Here, the far infrared spectrum of the molecule, we have been observed. Okay. And again, the Stokes and anti-Stokes lines are also found to be bands composed of rotational fine structure. Okay. Composed of rotational fine structure. So what are the characteristics we have seen is, first characteristic is under the low resolution, we have seen that Stokes lines and as well as the anti-Stokes lines, one Stokes Raman line as well as the one anti-Stokes Raman line, each having what we call same wave number, which are displacement having delta nu, which we have seen here. The previous one we have seen here. This is a delta nu. Okay, we have, and here also one delta nu we have, right? And this is due to what we call vibrational rotational absorption. This is due to vibrational rotational absorption band. Okay, in the near infrared spectrum of the molecule. So when we observe in the high resolution, under the high resolution, the exciting line is formed to have on both sides close, which are approximately equidistant lines you are going to be have. So this is pure rotational Raman spectrum. This is a pure rotational Raman spectrum. The spectrum between successive lines are in the far infrared spectrum of the molecule. This will be present in the far infrared spectrum of the molecule. Again, if you see about the Stokes and anti-Stokes lines, so here the Stokes and anti-Stokes lines are found to be bands which are composed of rotational fine structure, you have. Okay, so these are certain what we call important characteristics. That is a two important characteristics under a low resolution as well as the high resolution. Okay, so if you see the characteristics, one of them, so the frequencies of the Raman lines, depends upon the frequency of incident light. Okay, so here whatever we are going to get Raman lines, whether it may be Stokes, anti-Stokes lines, that is a low frequency or higher frequency. So thus the frequencies of Raman lines, we can say that the frequencies of Raman lines, the frequencies of Raman lines, they depend on the frequency of incident light. Okay, so whatever may be the frequencies which are getting the Raman lines, so the frequencies of Raman lines, they are dependent of the incident light, that is whatever may be the monochromatic light whichever we are incidenting, so on that frequencies they are going to be depend. Okay, that is a one characteristic of a Raman line we have. That is we have this one. And second one, if you see, in this case, the displacement of Raman lines from the original line means how much distance they are going to be have. Okay, the displacement of the Raman lines. Second one is, this is the second one, the displacement. The displacement of Raman lines, whichever we are getting due to the scattering Raman lines. Okay, so the Raman lines from the original line, that means at the center we have Rayleigh scattering, no? That is the Rayleigh, whichever we have, that is the original one we can call. So the displacements of Raman lines from original lines, they are dependent on the nature of the scattering substance. That means the light, whichever it is going to be incident on the material. So what type of material it is having, that means the nature of the material, it depends. Okay. On the other hand, we can say that the displacements of the lines are independent of frequencies of incident light. So here in this case, how much distance they are going to be moved. That means the displacement of the Raman lines, they are dependent on the nature of the material only. That is nature of the scattering substance only, not on the what we call frequencies of incident light. Whatever may be the incident frequency, whichever we have, so they don't depend on that one, but they are dependent upon only this what we call nature of the scattering substance. That is what we have. And one more characteristics we see here. The lines of greater frequency, as we said that you'll be having the lesser frequency as well as the higher frequencies we have been called. The greater frequency lines we have called it as what? Anti-Stokes we have been called. We called it as a anti-Stokes we have been called. So these anti-Stokes lines, while the lines of smaller frequencies are called Stokes lines. Okay. So anti-Stokes lines, you are going to get the higher frequency or greater frequencies you are going to be get. Greater frequencies you are going to be get. And the second one, the Stokes lines. The Stokes lines, whichever we are going to be have, they are going to be have what we call smaller frequencies. Smaller frequencies you have. You have the smaller frequencies. So this is about the Raman spectrum or Raman spectrum we have. So how we have been found. So here you see. So Raman spectrum, before going into the Raman spectrum, we said that we should know about the Rayleigh scattering. We should know. So what is Rayleigh scattering is, whenever a beam of monochromatic light is going to be passed through a gas, a liquid, a transparent crystal, a transparent solid body, whatever we are going to be have. So a small fraction of light is scattered in all directions. A small fraction of light is scattered in all directions. So the scattered light can be seen from the side of the substance. From the side of the substance, Rayleigh observed that in the spectrum of scattered light, there is a change in intensity, but there is no change in wavelength or frequency. That is, whenever the monochromatic light is hitting certain matter, which is, we can call it as a gas or liquid or transparent crystal, whatever we are going to be have. So whenever it is hitting on that one, it is going to be scattered. Amount of small fraction of light is going to be scattered in all directions. Okay, the scattered light can be seen from the side of the substance. We can able to see. So this Rayleigh observed that in the spectrum of scattered light, there is a change in the intensity. He observed that there is a change in intensity, but there is no change in the wavelength or frequency. He has not observed. So this is what we call it as a Rayleigh scattering we have been called. Okay, so Rayleigh scattering we have been called. So after that, Sir C.V. Raman has been observed that. So we otherwise we can say that some of the what we call scattering, which is inelastic scattering, also we are going to be have here. So Rayleigh scattering, whatever we are going to be get, that is a that is going to be, most of them are going to be scattered elastically. So, but a few undergo what we call inelastic scattering. Okay, so these inelastically scattered photons have frequencies lower and higher than the incident frequency, Okay, so these phenomenon is observed by Sir C.V. Raman in the year 1928, and this is what we call referred as a Raman scattering. Okay, this is referred as a Raman scattering. So the lines on the low and high frequency sides of the Rayleigh line are called it as a Stokes lines, and as well as the anti-Stokes lines respectively. They have been called it as a Stokes lines and as well as the anti-Stokes lines. So here you see, so this is the original according to the what we call a Rayleigh scattering. This is what we have, the original line. So there will be less frequency lines you are going to be observed, high frequency lines you are going to be observed. So this we have been named it as a Stokes and as well as the anti-Stokes lines they have been called. And this phenomenon has been observed by Sir C.V. Raman, and so that is the reason why we call it as a Raman spectra we are going to be called here. Okay, so and the main what we call there are two important characteristics we have. So that is what we have seen in the case of the Raman spectrum. So under the low resolution and as well as the under the high resolution. So the first one which we have seen is under the low resolution, there is one Stokes Raman line and one anti-Stokes Raman line, each having the what we call say wave number displacement of same wave number displacement of delta nu. So that is, you see a delta nu same we are having the left side displacement on the right side, that is nothing but the at higher frequencies also you have the same displacement, and at lower frequencies also you are having the same displacement you are going to be have. Okay, with respect to the original line. So this is vibrational Raman spectrum. Okay, this is vibrational Raman spectrum. So Raman displacement delta nu, whichever we have, agrees exactly with the wave number of the main vibrational rotational absorption. So here it is a vibrational rotational absorption, and that is a vibrational rotational absorption band, and which is in the region of near infrared, Okay, so near infrared we have. So this is one characteristic we have, and after that the second one important characteristic is we can say that when we have observed under the high resolution, this is under the high resolution whichever we have. So under this high resolution, the line which is found, original line, it is found to have on both sides approximately equidistant lines. On the both sides means original line is a Rayleigh scattering line we have, and left side lower frequencies and the right side higher frequencies, whichever we are going to be have. They observed approximately equidistant lines on both sides. On both sides, you are going to observe equidistant line. So this is due to we call it as a pure rotational spectrum. We are going to be called pure rotational spectrum, the spectrum between the successive lines in the far infrared region. The spectrum between the successive lines is in the far infrared. You are going to be have far infrared spectrum of the molecule. Okay, so the Stokes and anti-Stokes lines are also found to be bands. It is going to be found to be bands composed of rotational fine structure. Okay, so this is main two important features which we have. And then after, if you see certain things about Raman spectra, so we have seen that the frequencies of Raman lines dependent on the frequency of incident line. That means whatever may be the frequencies which we are getting for Stokes lines as well as the anti-Stokes lines. So these frequencies of the Raman lines dependent on the frequency of the incident light, that is the monochromatic light, whichever it is going to be incident on the matter or material, or the frequency of that light, it is going to be have the dependent upon what we call Stokes and as anti-Stokes line frequencies. So these Stokes lines and anti-Stokes lines frequencies dependent on the frequency of incident light. So this is what we have. And then after, we have the what we call second one, that is about the displacement of the Raman lines. Okay, about the displacements of the Raman's lines from the original line. So the displacement of the Raman's lines from original lines is dependent on the nature of the scattering substance. Okay, the displacement of the Raman lines, this is dependent upon the nature of the scattering substance. Okay, dependent upon the nature of the scattering substance. It depends on this one, but not dependent upon the frequency of incident light. It is independent. The displacement of the Raman lines is independent of the frequency of the incident light. This is what we have. Next one we have is the lines of the greater frequencies are called anti-Stokes lines. Already we have seen. And the small frequencies lines, we have been called it as a Stokes lines. We have been called. Okay, we have been called it as a Stokes lines. So suppose if you see about these Stokes as well as the anti-Stokes lines, if you see, so the fourth point whichever we have, so the anti-Stokes lines, okay, the anti-Stokes lines whichever we have, so these anti-Stokes lines are weaker than the Stokes lines. So these anti-Stokes lines are weaker than the Stokes lines. Anti-Stokes lines are weaker than Stokes lines. That point you have to remember. These are weaker than the Stokes lines we have. Next one is Raman effect is purely molecular phenomenon. You have to remember that this is a purely molecular phenomenon. So we have already seen about what we call a molecular spectroscopy as well as atomic spectroscopy. We have, whenever we have started the spectroscopy, we have been told that it has been divided into atomic spectroscopy as well as the molecular spectroscopy. So coming to this Raman effect, so this Raman effect is a purely a molecular phenomenon that you have to remember. So these are the 5 points which you have to remember. That is the frequency of Raman's lines dependent upon the frequency of incident line, 1 point. And second one, the displacement of the Raman lines from the original lines depends on the nature of the scattering substance, but not on the what we call frequency of incident line. It is independent of the frequency of incident line. Next, the third point is the lines of greater frequency are called as the anti-Stokes lines, and the lines of a smaller frequency we have been called it as a Stokes lines we have been called. And one more point, the 2 more points which are having are anti-Stokes lines are weaker than the Stokes lines, that you have to remember. And Raman effect is a purely molecular phenomenon. It is a purely molecular phenomenon. It does not go into atomic spectroscopy, all those things. So it is only about a pure molecular phenomenon. Okay. So this is about the Raman effect. Then after, we have like a classical theory of Raman scattering we have, and as well as the quantum theory of Raman scattering we have. Okay. We have classical theory of Raman scattering as well as the quantum theory of Raman scattering we have. So first we'll see about classical theory of Raman effect. Okay, so classical theory of Raman scattering. So first we'll see about classical theory of Raman scattering. So here in this classical theory of Raman scattering, an elementary explanation of the Raman effect. Okay, an elementary explanation of the Raman effect can be given by from classical theory. That is, elementary explanation of the Raman effect can be given by the classical theory. So here, suppose when a beam of visible light or UV light, okay, when a beam of visible in this classical theory of Raman effect, 1 minute. Okay, a beam of visible light or UV ultraviolet light. Right. So whenever these beam of visible or ultraviolet light which are falling on a molecule, that means the incident radiation is, whether it may be visible light or UV light, whenever it is hitting upon a molecule, what happens means there is a oscillatory electric field of the beam induces an oscillating electric dipole moment. That is, this light causes what the otherwise we can say that the oscillating, whenever these are hitting, you are going to get this what called oscillatory, okay, oscillatory electric field. Okay, so oscillatory electric field of the beam. The oscillatory electric field of the beam induces an oscillatory electric dipole moment. Oscillatory electric dipole moment. So that is, whenever the beam of light of visible or UV light is incidenting upon the molecule, the oscillatory electric field of the beam induces an oscillatory electric dipole moment in the molecule. Okay, then the molecules are said to be polarized due to this oscillatory electric field. They are said to be polarized. So here, 1 minute. Right. So here we have the molecule is said to be polarized, and the polarization P. Okay, 1 minute. Okay, polarization due to that oscillatory electric field, polarization P here, whichever we are going to be get. So this polarization P, whichever you are going to be get, that is, the molecule is said to be polarized, and the polarization due to that oscillatory electric field P is directly proportional to this. P is directly proportional to the applied electric field. E here. So simply we can write P is directly proportional to E you are going to be get. Okay, P is directly proportional to E you are going to be get here. Right. So the intensity of the electric field is directly proportional to the what we call polarization P, or we can say that magnitude of the induced dipole moment. Okay, so here this we are going to get it as, if you remove this this also we can write it as this, we can write it as a P is equals to alpha E. Here we can write. Okay. So this alpha, this is not alpha. This is directly proportional to E. If you remove this directly proportionality, we are going to get this alpha. So this alpha, we call it as a polarizability of the molecule. We call it as what? Polarizability. Polarizability of the molecule. We call it as what? Polarizability of the molecule we are going to be called here. So now, so as we said that the light which is going to be incident on the matter, okay, so that light we call it as a radiation, and if you the light which is we call it as a radiation. So when a radiation of frequency, nu naught, okay, nu naught is allowed to fall on the molecules, okay, it is allowed to fall on the molecules, then what happens means each molecule of the matter is going to be experiences a variety of electric field. What is that? So whenever a radiation of frequency, so this you can take it as this you can write it as equation 1. So whenever this radiation of frequency nu naught is allowed to fall on molecules, each molecule experiences a varying electric field. Okay, each molecule is going to be experiences a varying electric field. So that electric field, whichever the molecules are experiencing, we can write it as, in terms of mathematical expression, as E is equals to E naught cos 2 pi nu naught T, we can write. Okay, so this is the electric what we call field, okay, varying electric field of each molecule is given by E is equals to, here we don't have this one, so this is a frequency of incident radiation, this is here we have, so this is not to this one, this is another equation. So E is equals to E naught cos 2 pi nu naught T we have. Okay, so suppose here let capital Q, okay, so what I'm writing is capital Q here. So what is capital Q here? It is Q be the coordinates, otherwise normal coordinate associated with the particular mole of vibration of frequency nu m. Okay, nu m. So this is the electric field equation we have written. Now what we are writing is Q be the normal coordinates associated with a particular mole of vibration of frequencies nu m here, For this nu m, Q be the what we call normal coordinates which are associated with this nu m of the molecule. Then we can write this expression in mathematically as Q is equals to Q naught cos 2 pi nu m T here. Okay, 2 pi nu m T. So this above one is E is equals to E naught cos 2 pi nu naught T, and this below one is Q is equals to Q naught cos 2 pi nu m T we have. Okay, so now here the alpha, that is the polarizability of the molecule, can be expressed in terms of Taylor series, in the normal coordinates Q. So here alpha, what is alpha? Polarizability of the molecule. Okay, polarizability of the molecule, alpha can be expressed in Taylor series. In the normal coordinates. In the normal coordinates we can express. So how we can express that is as, 1 minute. How we can express is, I'll write here, 1 minute. That we can write it as alpha is equals to alpha naught plus, next one is dou alpha by dou Q, dou alpha by dou Q naught into Q plus so on here. Okay. So this is what actually the Taylor series in the normal coordinates. Alpha is equals to alpha naught plus dou alpha by dou Q naught Q plus and so on you are going to get. So now what we have to do is we will substitute this equation 2, equation 3, equation 4 in equation 1 we are going to be substitute because we have the E value that is the electric field E naught cos 2 pi nu naught T and as well as this polarizability we have expressed alpha value we have been expressed polarizability of the molecule we have expressed in terms of a Taylor series. So we will substitute all these in this equation 1. So if you substitute here, okay, if you substitute, you will be getting it as P is equals to, okay, P is equals to alpha naught plus dou alpha by dou Q naught into Q naught cos of 2 pi mu mt, okay, into this all we have into this electric field that is expressed E naught cos 2 pi nu naught into T, okay, 2 pi nu naught into T. So this we can write separately as alpha naught E naught cos 2 pi nu naught T plus next this is a plus dou alpha by dou Q naught. We have a E naught Q naught cos 2 pi nu m T plus T into cos 2 pi nu naught T we can write here. Okay. So here this we can write in terms of cos A cos B. This above equation we can write in terms of cos A cos B. That is cos A cos B is equals to, we have formula like a half cos A plus B plus cos of A minus B. What is that? We have cos A cos B is equals to half cos A plus B plus cos A minus B. So if you write that, finally we can write this as, P is equals to alpha naught E naught cos 2 pi nu naught T plus half this part, whichever we are writing cos A cos B, because we have in terms of cos A cos B, this one, this expression. So it will be dou alpha by dou Q naught into Q naught, E naught will take outside, both we have same. So it will be cos of 2 pi nu naught plus nu m plus into T plus 1 minute into cos of 2 pi nu naught minus nu m cos A minus B into T. Okay. So this polarizability, polarization P is equal to we have got. So the polarization of this, okay, the polarization of this, which is contains 3 distinct features. So if you see this equation here, okay, if you see this equation, in this equation, it is going to be have 3 varieties of this you are going to be get. So one condition what we are going to be have is, which is we call it as a nu is equals to nu naught. Nu is equals to nu naught. That is nothing but the frequency of incident radiation is equals to the frequency which we have after scattering. Then we call it as a Rayleigh line we are going to be called. Okay, Rayleigh line. So we said that in the case of the Rayleigh scattering, we don't have extra frequencies. The frequencies will be same. That is nothing but the scattered photons are having the same frequencies, but there is change in the what we call intensities only. That means there is no change in the frequencies. That is what we have written. Nu is equals to nu naught is nothing but the frequencies of incident photon and scattered photon is same, That is what we call it as a Rayleigh line we are going to be called here. Then after the second one which we are going to get is nu is equals to nu naught minus nu m. That is what we have seen here. Cos of 2 pi nu naught minus nu m. That is the second term of this equation. P is equals, we have the second term here we have. So this one, whichever we have, so this is what we call it as Raman's stroke lines. Raman Stokes line. So we said that in the case of the Raman Stokes lines, the frequencies of the Raman Stokes lines are lesser frequencies. So that is what we have. Nu is equal. So that is the frequency of the incident scattered photon is equals to nu naught minus nu m. That is original frequency minus nu m we have. That is nothing but lesser frequency. That is what we call it as a that is a Raman's Stokes lines we are going to be called. Next we have is the term is nu is equals to nu naught plus nu m. That is Raman's, we call it as a Raman anti-Stokes lines. Raman's anti-Stokes lines we are going to be called here. So we said that there will be anti-Stokes lines. So these anti-Stokes lines frequency is greater than the incident photons. So the scattered photons which are having the greater frequency, that is a nu naught plus nu m, we are calling it as a Raman's anti-Stokes line. So this is how the classical theory of Raman effect. This is what we have, the classical theory of Raman effect. So the classical theory of Raman effect also proved that there will be three lines of frequencies. That is the original lines of frequency we have. In addition to that, we have two different frequencies. One we called it as a Raman Stokes lines, which are having the lesser frequency than the original frequency. That is nu naught minus nu m. Then we have Raman anti-Stokes lines, which we called it as a higher frequency, which we are going to call it as a nu naught plus nu m. So that is classical theory of Raman scattering also proved the what we call a Raman effect. That is whatever we have seen about the Raman effect. So this is what we have, the classical theory of Raman effect. Next we have is a quantum theory of Raman effect. Okay. Next we have is quantum theory. So how it has been proved also important. According to the quantum theory of Raman effect. Okay, quantum theory of Raman effect. This we'll see here. So in the quantum picture, if you see, in the case of the quantum picture, radiation one minute. Quantum theory of Raman effect. 1 minute, I'll show you. I'll share. In the case of the quantum picture, radiation has both what we call particle as well as the wave nature. We have the particle as well as the wave nature we have. Particle as well as the wave nature we have.
వాయిస్ రావట్లేదు సార్. వీడియో రావట్లేదు సార్.
చాలా గట్టిగా మాట్లాడు. Bless. Yeah, you laugh. SMJ ఇచ్చిండు కాకి మీరు తీయాలి మమ్మీ ఒక రబ్బు వేసిన రబ్బు మమ్మీ
క్లాస్ రావట్లేదా సార్?
మేడం అసలు సార్ కి ఆడియో వీడియో కనెక్షన్ లేదు. చూడండి ఒకసారి పార్టిసిపెంట్స్ లో చూస్తే అసలు సార్ ఏమీ కనిపించట్లేదు, మైక్ వీడియో ఏమి కనిపించట్లేదు.
అవును మేడం.
సో సార్ ఏమన్నా కాల్ మాట్లాడుతున్నారా? మరి కాల్ మాట్లాడినా అట్లా రాదు. అంటే దీంతో చాప్టర్స్ మొత్తం అయిపోయినాయా మేడం? మీరు విన్నారా? గుడ్ మార్నింగ్ మేడం.
లేదు మేడం,
Hello.
ఇవాళనే స్టార్ట్ నేను వినడం కూడా.
కదా
ఇవాళనే
అవన్నీ
వింటున్నా.
ఏంటి మరి అందులో జరిగింది? ఇవి ఆన్లైన్ క్లాసులు ఆఫ్లైన్ క్లాసులు ఇంతవరకు జరిగినాయి మేడం?
తెలీదు మేడం, నేను ఇవాళ స్టార్టింగ్ అంటే ఒక 10 minutes తర్వాత స్టార్ట్ చేసిన నేను కూడా.
అవునా, మరి డైరెక్ట్ లాస్ట్ చాప్టర్ కి వచ్చేసింది సార్.
అవునా, అంటే మొన్న ఒక పోయిన
ఆఫ్లైన్ క్లాసెస్ లో సార్ సెకండ్ యూనిట్ థర్డ్ యూనిట్ కంప్లీట్ చేశారు.
అవునా మేడం.
అవునండి, ఇది ఆన్లైన్ క్లాస్ లో ఈ రోజు మళ్ళీ క్లాసెస్ ఉన్నాయి. ఈ రోజు 4th యూనిట్ లోకి వచ్చారు. సెకండ్ థర్డ్ ఆల్రెడీ కంప్లీట్ అయిపోయింది.
మేడం థ్యాంక్ యూ మేడం. అండ్ మనకి ఎప్పుడు ఎగ్జామ్స్ ఉంటాయి మేడం? నాకేం తెలియక అడుగుతున్నాను.
మోస్ట్ ప్రాబబ్లీ మేలో ప్రాక్టికల్స్ ఉంటాయి అంటున్నారండి. జూన్ లోనో జూలైలోనో పెట్టేయచ్చేమో ఈసారి ఎగ్జామ్స్ అంటున్నారు.
మేడం ఎక్కడి నుండి మీరు? దుర్గాదేవి గారు కదా?
నేను హైదరాబాద్.
మేడం మాది బ్రాంచ్ వరంగల్ బ్రాంచ్ మేడం. అంటే డిఫరెంట్ టైంలో కండక్ట్ చేస్తారు కదా ఎగ్జామ్స్.